Poisson distribution. Let's talk about Poisson distribution now, where basically in the Poisson distribution, we try to find out the distribution for the number of successes and average rate of success. So, in the Poisson distribution function, it finds the probability that a certain number of successes occur based on an average rate of success. In other words, we can say as this function returns the value of the Poisson probability density function. So the name of the function is dpois, and dpois has two parameters. The first one is x and the second one is lambda. X is the number of successes and lambda is the average rate of success. In this example, we are finding the probability using the dpois function to get exactly 12 sales if the person makes 30 sales each hour in the hour. So basically, the question is, we are trying to find the probability where exactly 12 sales is done if the person makes 30 sales in every hour. We can see dpois is equal to x equals to 12, which is the exact sales. Lambda is equal to 30. So we can see over here that the output is 0.0001. We can see over here that the output is 0.0001 and the function is dpois. So mainly, if we have a good hands-on knowledge of Poisson distribution, we can call this dpois function very easily with just two parameters, where the first one is x, which is the number of successes, and lambda, which is the average rate of success. We have done Poisson distribution in statistics, and there if you correlate with the formula, you will find that in R, it becomes extremely easy to understand and evaluate the distribution. Next, we have ppois function. This function finds the probability that a certain number of successes or less occur based on an average rate of success. In other words, we can say as this function returns the value of the inverse Poisson cumulative density function. We can see over here ppois is equal to q minus lambda. Now, q is the number of successes and lambda is average rate of success. We can see q is my number of success and average rate of success is lambda. So, considering the example, in this example, we are finding the probability using ppois function to get sales or less if the person makes 30 sales each hour in the hour. So you can see over here that ppois is equal to q equals to 12 and lambda equals to 30. You can see the output 0.0001. We can see over here that q is 12 and lambda is 30, where the person makes 30 sales each hour. Next, we have the qpois function. In the qpois function, find the number of successes that corresponds to a certain percentile based on an average rate of success. In other words, we can say as this function returns the value of the inverse Poisson cumulative density function, the syntax is qpois within brackets p, which is percentile, and lambda, which is average rate of success. So in this example, we are finding the probability to get the sales needed to be at the 80th percentile for the sale in an hour. So if the person makes 30 sales per hour in the hour, we will find out qpois p equals to 0.8, which is the 80th percentile. Lambda is equal to 30. So the output is 35. You can see over here p is equal to 0.8 and lambda equals to 30. So that is how we are trying to have a function which is qpois function. Next, we have the rpois function. Now, this function generates a list of random variables that follow a Poisson distribution with a certain average rate of success. In other words, we can say as this function generates a vector of Poisson distribution random variables, we can have rpois with n and lambda. So we are having the random distribution. So there the first parameter definitely becomes n, which is number of random variables to generate, and lambda, which is the average rate of success. So let's consider the example. In this example, we are generating a list of 20 random variables that follow a Poisson distribution with a rate of success equal to 6. So you can see I'm calling our Poisson function, and within the function n equals to 15, which is my number of random variables to generate, and lambda equals to 6, which is the rate of success. So rate of success is equal to 6. You can see over here the output, which is 59477 968 439 3229. So you can see over here, this is my Poisson distribution. Let's understand plotting Poisson distribution using R function. Now, we have to plot the distributions, and distribution plotting is also quite a simple task. But the only prerequisite is that we have to understand the basic functions and the basic concept of Poisson distribution. So, to plot the probability mass function for a Poisson distribution in R, we can use the following function. Dpois within brackets x comma lambda to create the probability mass function. After that, we have plot x comma y type equals to h to plot the probability mass function, specifying the plot to be a histogram. So in that case, type equals to h. Now, to plot the probability mass function, we simply need to specify lambda, that is the rate of occurrence of events in the Dpois function. And you can see the graph in the output, which is a Poisson distribution. Now, let's understand the same with the help of an example. So this example has a code which illustrates how to plot a probability mass function for a Poisson distribution with lambda 5. Very simple. Define the range of successes. The range of success is from 0 to 20. Create plot of probability mass function. Plot success, comma, Dpois, success, comma, lambda equals to 5. So we have success and Dpois success, lambda equals to 5 with the average rate of success is 5 and type equals to h. So you can see that we have plotted the graph. Now, let's talk about visualize package. What is visualize package? So normally visualize package is a package that we have talked about, that these are the inbuilt features and the functions which are available, and we can install them and then we can use them. So how to install visualize package? You can install the released version of visualize from CRAN. So we all have talked about CRAN, and here we are installing with install.packages command, which is a function, and within the brackets I am passing visualize, which is the name of my package, and the development version from GitHub with install.packages within brackets DevTools. So how I'm visualizing, how I'm downloading DevTools : install _ GitHub, which is a function. So in the brackets I am writing /visualize. So basically these are the few commands that we have to understand and load the packages, and after installing the packages, we can always use the features of visualize package and create our graphs. Now let's talk about library.visualize. If we see that what we have done with library, we were loading the packages with the help of library function. So now we have loaded the package. Then construct a graph by following the visualize.distribution pattern. So here we see that normal distribution can be shown with graph, a standard normal distribution with a z-score of 1.96. So visualize.norm within brackets 1.96. Change the location of the tail, visualize.norm 1.96, comma, section equals to upper. Shift the mean and create a bounded range, visualize.norm C and within brackets minus 1.96 to 1.96. Section is bounded. So you can see over here that how I'm calling the norm function of visualize package, and I am creating a graph with a z-score of 1.96. I have also changed the location of the tail, and I have shifted the mean and create a bounded range. Let's have a look of the parameters to be distributed, that how it can be modified. So take the example for binomial distribution. Visualize.binom equals to stat equals to 9, size equal to 20, and p equals to 5. Likewise, visualize.binom is equal to stat equal to 9, size equal to 24, and p equals to 0.25. Discrete distribution can also handle a level of strict less than, greater than, or equal to, less than, equal to, or greater than, equal to, inequality. Visualize.poise, stat equals to 4 to 6, lambda is 3.5, and section is bounded. Strict equals to true, true. Visualize.poise, stat equals to 4, 6, lambda is 3.5, section is bounded. Strict equals to true and false. Visualize.poise, stat equal to 4 to 6, lambda is 3.5, and section equals to bounded. So that is how I am creating discrete distributions. And now strict is a function which is used where I am passing false and false. So students, I hope you all are able to understand the concept of distribution and how we can create these distributions with the help of R programming and display certain graphs, or we can say the charts, very easily. The only prerequisite over here is that you need to have good hands-on experience on statistics and the distributions. When you are clear with the concepts of distributions, these functions will look very simple, because the concepts like lambda, or the concepts like number of occurrences, true, false, or maybe sample size, are all statistical techniques and the words which are commonly used in statistics. Once we are clear with that, it will become very easy for us to try these functions and see the beautiful outcomes on the screen. With this, I end this lecture. Stay tuned for my next lecture. Thank you.